Hi everyone, and welcome to our first lesson on ultrasound physics. In this video, we'll cover the fundamental principles that form the basis of ultrasound imaging. Whether you're just starting out or looking for a refresher, you're in the right place. Let's dive in. Before we get into the physics behind ultrasound, let's understand what ultrasound is. Ultrasound refers to sound waves with frequencies higher than the upper audible limit of human hearing. And in medical imaging, we use ultrasound to visualize internal structures of the body in real time. Some key points to note are that ultrasound operates at frequencies greater than 20,000 Hz, which is beyond the range of human hearing. And in contrast, audible sound, like the sound of my voice or music, typically ranges from about 20 to 20,000 Hz. This audible range covers the frequencies that we can hear with our ears. Now on the lower end of the spectrum, we have infrasounds, which consists of frequencies lower than 20 Hz. Now let's talk about how ultrasound imaging works. Ultrasound machines emit high-frequency sound waves, which penetrate into the body and bounce off of tissues. And these echoes are then detected by the ultrasound transducer and converted into electrical signals, forming an ultrasound image. Now in this first chapter, we're going to discuss sound waves and how they form the foundation of ultrasound imaging. Sound waves are mechanical vibrations that propagate through a medium such as air, water, or solid materials. And there are different characteristics of sound waves that are important for us to know, and we refer to them as acoustic parameters. Now let's begin with frequency. Frequency refers to the number of cycles per second in a sound wave and is measured in units of hertz. In diagnostic imaging, ultrasound machines typically operate within a frequency range of 2 to 15 megahertz. Now, why does frequency matter in ultrasound? Higher frequencies result in better resolution, just like how we have high resolution on our cameras to get the best quality photos. High-frequency ultrasound waves can see tiny structures within tissues, providing sharp and detailed images. However, there's a catch. You know, when you zoom in too much on your camera, you can sacrifice the overall clarity. Higher frequency sound waves have very limited penetration. They're great for imaging superficial structures close to the skin surface, but they struggle with penetrating deeper tissues. Now, let's switch gears and consider lower frequency ultrasound waves. These waves have the advantage of better penetration. Lower frequency waves can travel deeper into the body, reaching organs and structures located further beneath the skin. So while they may not offer the same level of detail as higher frequencies, they provide valuable information about deeper anatomical structures. So in ultrasound imaging, it's all about finding the perfect balance. Just like adjusting the camera to capture the perfect shot, choosing the appropriate ultrasound frequency allows us to balance resolution and penetration, ensuring that we obtain clear and informative images tailored to each diagnostic scenario. It's important to note that frequency is determined by the ultrasound machine's sound source, and the next time you're scanning, remember that the frequency influences both resolution and penetration, playing a very important role in diagnostic accuracy. Now let's dive into the concept of period, which is the time it takes to complete one cycle of a sound wave. And unlike frequency, which measures how often a cycle occurs per second, period focuses on the duration of a single cycle. And of course, since we're talking about duration, we measure period in units of time, such as seconds, minutes, or even hours. Now here's an interesting relationship. Period and frequency are inversely related. Now, what does that mean? Well, imagine a seesaw. When one side goes up, the other side goes down. This is a simple way to describe an inverse relationship. When the frequency is higher, the period is shorter, and vice versa. And in ultrasound imaging, period is determined by the sound source, and it's not something we can adjust during the imaging process. So while we might not directly set the period on our ultrasound machines, understanding this concept helps us to appreciate the relationship between frequency and period. Now we're going to explore the concept of wavelength, which is the distance or length of one complete cycle of a sound wave. In other words, it's the distance between two consecutive points in a sound wave that are in phase, such as from one peak to the next peak, or from one trough to the next trough. Now, wavelength is measured in units of length, such as centimeters or millimeters. Now, here's another important relationship to understand. Wavelength and frequency are inversely related. This means that when frequency is increased, the length of the wave is shorter, and vice versa. So higher frequency corresponds to shorter wavelengths, and lower frequency corresponds to longer wavelengths. One key thing to note is that wavelength is the only acoustic parameter that's determined by both the sound source and the medium through which the sound waves are traveling. Now we're going to talk about amplitude, which represents the maximum displacement of particles in a sound wave from their resting position. Now, amplitude determines the strength or intensity of the ultrasound wave, and typically it's in units of decibels. Now, amplitude can be measured from the baseline to the maximum value, or from the baseline to the minimum value. Now let's illustrate the concept of amplitude with a simple analogy. So imagine you're at a concert and the sound of music is filling the air. Now picture two scenarios. In the first scenario, the band is playing softly and the volume level is low. Here, the sound waves have low amplitude, meaning they're not displacing the air particles very much from their resting positions. So as a result of low amplitude, the music sounds very quiet. Now let's say the band cranks up the volume and the music becomes louder and more energetic. In this case, the sound waves have higher amplitude, causing greater displacement of air particles and producing a more intense sound. So just like adjusting the volume on your stereo system controls the amplitude of the sound waves, amplitude in ultrasound imaging helps us to control the intensity of echoes and visualize structures within the body with clarity. A key thing to note here is that in ultrasound imaging, amplitude actually influences the brightness of the image, which is something that we'll talk about in later videos. Now, let's explore the concept of power. Power represents the rate at which energy is transferred or the rate at which work is performed, and it's measured in units of watts. Now here's the key point. Power is directly proportional to the square of the amplitude of the wave. So in simpler terms, when the amplitude of the wave increases, the power of the wave increases exponentially. So if we double the amplitude, the power of the wave actually increases by a factor of 4. This means that doubling the amplitude results in a quadrupling of the power. So we've talked about inverse relationships already. Now let's discuss direct relationships. Now when two things are directly related, it means that as one increases, the other one also increases. And as one decreases, the other one decreases as well. In other words, there is a linear relationship between the two variables, where changes in one directly result in corresponding changes in the other. Now let's talk about intensity, which refers to the concentration of energy in a sound beam, and it's measured in units such as watts per square centimeter. Now here's the key point. Intensity is directly related to the power carried by the wave and inversely related to the area through which the wave is spreading. Imagine shining a flashlight. As you focus the light into a smaller area, the intensity of the light increases because the same amount of light is concentrated over a smaller space or area. Similarly, in ultrasound imaging, focusing our ultrasound beam on a smaller area can result in clearer images. However, controlling intensity is crucial in diagnostic imaging. High intensities can result in tissue heating, which can produce harmful effects, and we need to be mindful of this. We will explore intensities and bioeffects in depth in a later video. Another important thing to note about intensity is that just like power, it is directly proportional to the square of the amplitude. So let's say that the amplitude increased by a factor of 3, the intensity would actually increase by a factor of 9. So remember, both power and intensity are directly proportional to the amplitude squared. The final acoustic parameter that we're going to talk about is propagation speed. And propagation speed refers to the speed at which sound waves travel through a medium. Propagation speed is measured in units such as meters per second or millimeters per microsecond. And in soft tissues, the propagation speed of ultrasound waves is typically around 1,540 meters per second. Now here's the key point. Propagation speed is determined by the properties of the medium through which the sound waves are traveling, such as density and stiffness. Now, stiffness refers to an object's rigidity or its ability to resist compression, while density refers to the amount of mass or relative weight of an object. In materials with high stiffness, such as bone, sound waves propagate quickly due to the efficient transmission of energy through tightly packed particles. Let's compare the experience of walking on a wooden floor versus walking on a mattress to understand how stiffness and density affect the speed of sound in a medium. Imagine walking on a wooden floor. The floor is rigid and stiff, and the sounds of your footsteps resonate clearly through the floor, and you move forward with ease. The floor represents a medium with high stiffness, and sounds travel faster. So since the speed of sound increases with more stiffness, this means that they are directly related. Now let's switch to walking on a mattress. The mattress is soft and yielding, and with each step, your weight sinks into the material, absorbing the impact. Your footsteps are muffled, and you move more slowly compared to walking on the wooden floor. The mattress represents a medium with low stiffness but high density, and with high density, the speed of sound decreases. Therefore, density and the speed of sound are inversely related. As we conclude this chapter on ultrasound physics, we've covered essential concepts that form the foundation of ultrasound imaging. We've learned how frequency affects resolution and penetration, and how stiffness and density influence the speed of sound in tissues. Each of these concepts are very important when it comes to understanding sound waves. And in the next chapter, we'll explore pulsed waves, building upon the knowledge that we've gained here. Until then, keep learning and keep scanning. Thank you guys so much for watching my video. If you like this content, don't forget to hit that like button and also subscribe to my channel. See you next time.